Okay, looks like we are live. Good morning, everyone. Thank you all for joining us today. My name is Gabriel Lopez. I'm Vice President for Research at the University of New Mexico. And next slide, please. It's my pleasure to be the co-chair of this virtual conference with Dr. Joachim Spatz. We've both been developing biomimetic environment-inspired material systems over the course of our careers. And over the past few years, we are now turning to synthetic material systems that begin to emulate cells and organelles, which is the topic of this virtual conference, bottom-up synthetic biology. And so welcome to the SynCell2020 virtual symposium. It is the International Conference on Engineering Synthetic Cells and Organelles. This virtual symposium is the product of quite a long effort to develop a conference on synthetic cells and organelles, an international conference, that is. It really began a couple of years ago. The actual origins of this conference and the idea date back to the establishment of NSF of their big ideas, one of which was understanding the rules of life a few years ago. At the same time, the Max Planck Institute was beginning their school Matter to Life, which you'll hear about today. In the course of the development of that school Matter to Life, at the University of New Mexico, we were visited by a longtime friend from University of Heidelberg, Dr. Michael Grunza, who was recruiting for this new school. And so while he was here in New Mexico, the NSF announced a new grant program called Design C3, which is part of their rules of life. And as part of that competition, there was an opportunity to apply to start a new conference. And so that's how we were funded, primarily to have this conference. It was originally planned for an in-person conference, but of course the COVID-19 interrupted our plans. In the original conference, the partners were to be the National Science Foundation, the University of New Mexico, the Max Planck School Matter to Life, Los Alamos Laboratory, Center for Nonlinear Studies, and the New Mexico Consortium. So we have received very generous support from all of these institutions, and we are quite grateful for that support. To provide a context for the technical field of bottom-up synthetic biology, I will now turn over the presentation to my co-chair, Dr. Joachim Spatz.
Yeah, so also hello from my side. Welcome to our virtual conference. I'm sitting here in Germany, actually at the Max Planck Institute in Stuttgart. So that's what webinar is able to do, the digital conference. And I will use now some minutes to introduce the topic a bit and the question about what is matter to life. For us, it's about very simply bringing molecules and technologies in a very smart way together to build lifelike systems. And in particular for this conference, lifelike systems will be synthetic cells. But that goes then on that it also allows building synthetic systems or synthetic cells allows to foster understanding of living systems, because we will learn by bringing these molecules together, we will learn how they eventually also operate in living systems and living cells. So it's a back and forth about understanding living systems, which will initiate, stimulate, to synthesize lifelike systems. And by building them, we will also learn and get input into understanding living systems. So it's a back and forth. And what are challenges of this field? And this is a very short list. There are many, many more, but I think challenges you can name, like how to build functional compartments. At the end, a synthetic cell is a compartment, or a living cell is a compartment which is very functional. And the question is, how can we build a functional synthetic compartment which operates lifelike, and maybe even beyond that, maybe it operates at conditions where a living system or a living cell could not operate. The question how to control replications, cell division, is unsolved. How to harness information transfer, how can information be passed from one division to another one. In synthetic cells, we don't know how to do this yet. How can we assist adaptations? So if you look at stem cells, which has a huge complexity, but stem cells, of course, can adapt to different environments. How can we realize this in synthetic cells is unsolved. How can we understand and control decision-making, what living systems are doing? This is unsolved in synthetic systems. And all this is dependent, of course, on energy. How can we create an artificial energy supply? The systems need to self-sustain it themselves, and that requires energy. So these are a few, I think, topics where I think the field has to answer with the coming years. And to me, it's very obvious that these questions will not be solved by one particular discipline. It strongly needs, it's a true interdisciplinary engagement what is required here. It will be based on core disciplines like physics, chemistry, and biology, but it also includes engineering, molecular systems engineering. And I think these are the four main pillars which eventually will solve questions I just raised. There are examples, worldwide examples of centers which already started activities in building synthetic lifelike systems. Like the Max Planck Society started in 2014, the Max in Bio program. Then out of the Max in Bio program, we then started the Max Planck School, Matter to Life, in 2018. There is the Molecular Systems Engineering Center at the ETH Zurich, with location in Basel, which started very early to look on engineering and how to build synthetic systems. Then there is, in the Netherlands, they have a long-lasting tradition in developing synthetic systems. And in 2017, they started the basic program, building a synthetic cell. Then in the US in 2017, the Build a Cell program started. And then the Max Planck Society has another program started together with the Bristol University. It's a center, it's a very small center, which is focusing on minimal biology. These are a few centers which I can highlight, which I know about. There are probably more, but this shows that this is really a starting field. And it's a global field, and it's very interdisciplinary. So SynCell2020, due to the corona virus pandemic, we have to go virtual. And the question is, so what do we lose actually by going virtual? And of course, we are losing in-person interactions. So obviously these distances are not possible anymore, no matter where you are in the world. We losing that maybe speakers are hesitating showing preliminary unpublished data because these virtual meetings are usually recorded, as it's with SynCell. But even if it's not announced that it's recorded, maybe someone else can record it from the screen. So you might hesitate showing preliminary unpublished data. You are losing concurrent sessions, but that eventually could be solved in the future. Also having poster sessions could be organized also by a virtual meeting. And of course, social activities we are missing, like there will be no conference dinner tonight. And this is, of course, all these are points which we miss greatly. And last but not least, I mentioned the conference dinner, and since this conference was meant to be in Santa Fe, and Santa Fe is of course known for very spicy and excellent New Mexican food. And I have 2 co-workers in my group, and they are suffering a lot being here in Germany and having not access to original New Mexican food. So that's what we lose, but there are other things we gain from a virtual conference. One is we get more and different participants, and we will show numbers also. And we will enhance speaker interaction. So usually what we learned with webinar, that there are easily 40 questions placed after a talk, and the speaker might answer all the questions, maybe not immediately, but during the next 24 hours by email. So there's a much stronger interaction possible. We have access to, we give access to science to very different audience. That means it's not limited by budget or by institutions or origin that you can participate in these meetings. Also, if you have to care for child, it's usually a big issue that you have to organize childcare, and that might then cause that you cannot participate in conferences, in physical conferences. But with virtual conferences, of course, this is possible. You can continue doing your experiments by staying at home, not traveling. You just can keep on running your experiments. It's for PhD and postdoc sometimes very essential not to lose too much time, but still getting access to information from conferences. Eventually, the recorded talks can also be used maybe in classes at universities or colleges in the future. So that it's a talk which you eventually give, is not simply lost. And eventually we reduce tremendously costs, and eventually also contribute to, by reducing flights, for instance, that we reduce carbon emission. And to give you these numbers, and I think these are really impressive. Today we are looking at 583 participants. So if all of them are online, we are now we have access to 583 participants, and they are coming from 6 continents, from 44 countries, from 180 institutions. So that these are numbers which we could have never reached in a physical conference. So it is about 500% more, five times more participants than we would have originally had at Santa Fe. And another number which is very impressive to me is that about 80% of these participants are postdocs, PhDs, undergrads, and even high school students are online here. And these usually cannot so easily travel to conferences. So we really make access, we allow the access to many more participants. And if you calculate this in US dollars, so we are saving, if you just calculate travel and hotel, we are saving about $1 million US. It's a huge number that in principle, of course, you can fund 32 PhD students for 1 year out of this. Or if you are into PDMS science, you can buy 13 tons of PDMS, which will last for some time. And eventually, the reduction of CO2 just because we are reducing traveling is 1,500 tons, which is another, I think, amazing number. So there are many benefits we gain from virtual conferences, but I would not say that virtual conferences will now in the future replace physical conferences totally. It's maybe competitive in terms of that some conferences will be only virtual. But I think the other format which will be the future is that you have physical conferences, but also virtual conferences in parallel, because this virtual part will allow so many participants to access without traveling, without having visa issues, without having budget issues. So I think the combination of having a physical conference and a virtual conference together might be the future. And I want to say that this idea of having our SynCell conference virtual is not built on Gabriel, it's not built on my idea. It's eventually really has been initiated by these two excellent postdocs from my group, Andrew Holly and Jennifer Young. So they approached me, and already before the coronavirus, they said, actually, they want to make a webinar conference. And now with the coronavirus, this was the initial key that they could convince us doing it virtual. And they organized everything. They are making it possible that the system runs. So we are really grateful of having them and making this possible for us. I'm really excited about this virtual conference. And I think with this, I hand over again to Gabriel, and he will add a few more comments.
Thank you, Joachim. So I would just like to briefly go over the agenda for today and for the next 2 days. You see here the schedule for today. Basically today, we will start with a couple of tutorials, one from Reinhard Lepowski from the Max Planck Institute of Colloids and Interfaces, and another one from Karin Jacobs from University of Saarbrücken. Both Reinhard and Karin, I believe, are members of the Matter to Life Consortium, and so today really highlights the Matter to Life program. Michael Grunze will give a highlight on the program itself and how it works. And then finally, we will end with a keynote lecture by Joachim Spatz on bottom-up assembly of a cell. Next slide, please. Tomorrow, the highlight will be the basic program. So we'll start with 2 tutorials, one by my colleague Darko Stefanovic from the University of New Mexico, and another from Jim Werner from Los Alamos National Laboratory. The basic program highlight will be delivered by Marilyn Dogterom from Delft University of Technology, who will also be presenting the keynote tomorrow on building a functional cytoskeleton in synthetic cells. And then on the third day, the emphasis will be on the Build-A-Cell network that Joachim mentioned. So we will start off with the keynote on Thursday, and that will be delivered by Drew Endy from Stanford University, the title being Upwelling: Challenges Arising from the Bottom of Earth's Life Well. It will be followed by a couple of tutorials. The first one will be by Laura de la Porte. She's from the Leibniz Institute for Interactive Materials in Aachen. And then the second one will be by my colleague, Nick Carroll from the University of New Mexico. And then Kate Adamala will present the program highlight on Build-A-Cell. And we will end the technical program with a panel discussion on future synthetic cell technologies for mitigation of viral pandemics. So that is what we plan to do over the next 3 days. I would like to remind everyone, next slide please, that we do intend to have the physical conference next year, as Joachim mentioned. So we're still planning on Santa Fe, and hopefully we will be able to see people here in New Mexico and enjoy breaking of tortillas together. This poster here was a poster for what we intended to be our physical conference this year, but as we have said, it had to be postponed, and so we're looking at spring 2021 in Santa Fe for the physical conference, and we hope that this virtual conference will serve sort of as an appetizer for the in-person conference next year. Please keep your eyes on our website, SynCell2020.unm.edu, for the latest information as it becomes available with regards to our physical conference, and we hope to see you there. Next slide, please. Okay, so a couple of technical points about how you can participate today in this virtual conference. The first one is if you would like to submit questions, at the bottom of your screen there's a question box, and so you can type your question into the box and then send, and the questions will be handled by the moderators. They will read the questions, and they will decide which questions to ask the speaker based on basically the relevance of the question, but also the popularity of the question. So the other thing that you can do in the icon, there's a thumbs up icon below each question. And so you can click on this if you like the question, and basically the more thumbs up the question gets, the more a question will move to the top of the queue and be likely to be asked by the moderator. In the event that we don't have time to answer all the questions, this will also prioritize the most in-demand questions, and we can ask the speakers to answer these questions with either posting replies either on the website or by email in the reply. And then finally, if you would like to see how many people are participating in the program, you can see that at the top of the screen. Next slide, please. So that's where you would see how many are here. Next slide, please. So I think that covers all of the logistics. I'd like to just end by acknowledging many people who have contributed to making this event a reality. For the virtual conference itself, as Dr. Spatz mentioned, Dr. Jennifer Young and Dr. Andrew Hollett have really been the drivers with regards to the idea and also putting together the technology for this virtual conference, and we're very grateful to them. At UNM, there's been a lot of work with regards to planning, dissemination of information, and arranging for speakers and moderators and panelists. And so I'm particularly grateful to Ms. Emily Ballo, Dr. Mary Jo Daniel, and Pamela Garcia Ramirez for their work really over the last full year. Finally, or rather, not finally, but we have also had an organizing committee that's been very instrumental in putting together the program. And so didn't have space to list all of the organizing committee, but I would like to thank them for their gracious contribution of their time and expertise. The organizing committee can be found on our website. And finally, we are very grateful to the speakers, the panelists, and the moderators who have given their time today and in the run-up to this virtual conference to put together high-quality presentations and share with us the latest in the state of the art on this area of bottom-up synthetic biology. I believe that is the last slide. Oh, no, one more, okay. So this is a picture of the mountains near Santa Fe, New Mexico, and we would really like to see as many people come to Santa Fe next year to enjoy not only the good food, but also the scenery and the great company of our fellow researchers. At this point, we will wait till exactly 8:30 to begin the proceedings today. I'm very happy to pass this presentation on to my colleague, Susan Atlas, who's a professor of biology, I'm sorry, of chemistry and physics here at the University of New Mexico. So I believe we will start at 8:30, but Susan, if you'd like to give some preliminary remarks, that would be great. Thank you all.
So good morning, everyone. I hadn't really prepared any particular remarks, but I would like to join Gabrielle and Joachim in welcoming everyone to the International Conference on Engineering Synthetic Cells and Organelles. It's a great pleasure to be the moderator for this first session and first day of this virtual conference. And as Joachim and Gabrielle said, hopefully this will be the start of many great things. And we hope to see everyone here in beautiful New Mexico next year. It will be very nice to also be able to interact with many of you in person. So I think we're going to start in just a second. I think we're going to take a 3-minute break, and then we'll go ahead and I'll be back on at exactly 8:30 so that we can stay precisely on schedule. So welcome everyone, and see you in just a few minutes. So welcome everyone again. We're going to go ahead and start the session. Again, just to remind you, please feel free to type in your questions during the talk, and we will have a 30-minute presentation followed by 15 minutes of questions. So it is a great pleasure to introduce Professor Reinhard Lipowski. Dr. Lipowski is director at the Max Planck Institute of Colloids and Interfaces and heads the Department of Theory and Biosciences. Dr. Lipowski did his doctoral studies at the University of Munich, where he was also professor of theoretical physics during 1989 and 1990. From 1990 until 1993, he was director at the IFF Research Center Jülich and professor in the University of Köln. He is a member of the Berlin-Brandenburg Academy of Sciences and has an honorary professorship at the University of Potsdam and the Humboldt University Berlin, and is the speaker of the International Max Planck Research School on Multiscale Biosystems. This morning, he is going to give the inaugural presentation at this inaugural virtual conference. His tutorial is on understanding and controlling the morphological complexity of biomembranes. Dr. Lipowski.
Thank you for this kind introduction. Can you hear me? So it's a pleasure to participate in this Corona-proof meeting. Of course, I would have liked to go to Santa Fe in person, particularly because of the jumpy ride over the mountains, but we will maybe do this next year. So what you see here on the first slide is the roadmap, or if you like, the headlines. So I will start with some introduction here on biomembranes and giant vesicles. I will then focus on some key concepts on which we have worked during the last couple of years. And so I will start with the introductory part. Well, before I actually go to membranes, I will just tell you that we have worked on 3 basic modules over the last couple of years. One is membranes, in particular giant vesicles, also on direct transport by molecular motors, and protein synthesis by ribosomes. Now, membranes are presumably the oldest module of this sort, and I will actually focus on it because during the last couple of years we have seen a very nice interplay and communication between theory and experiment. So we can do quantitative parameter estimates, and we can go from understanding to construction. Now, membranes are multi-scale systems. So this is just a reminder, starting with a simple lipid bilayer, has about a thickness of 4 nanometers. Of course, this is a very simple one-component lipid bilayer in this cartoon. Now, if you go to cellular membranes, it's decorated by all kinds of proteins which are inserted into the membrane or anchored at the membrane, and there might be also sugar groups and so on and so forth. And then if you go to quite a bit larger scale, you will see organelles like the endoplasmic reticulum. And here I basically show you an old or canonical view of the endoplasmic reticulum compared to a quite more recent view, which now sort of use the ER. These are the blue lines here, which are tubular membranes which form a network and get into contact with all kinds of other organelles by so-called membrane contact sites. So let me just remind you that we go here from 4 nanometers to maybe 40 micrometers. Another important background information is that biomembranes are fluid. So if we color 2 lipids in the lipid, in the bilayer, let's say the violet and the green one, it would take about a nanosecond, of the order of a nanosecond, that they would swap their location. In fact, they have a diffusion constant which is of the order of micrometer squared per second. And this fluidity has a number of important consequences. So one is that because of lateral diffusion, you can have responses of the bilayer in terms of composition. You can have demixing, as you see here, or you can have domain formation, depending on the forces or perturbations which come from the external media. And in addition, because of solidity, these membranes are very flexible. So you have lots of morphological responses, budding, tubulation, which provide direct evidence for fluidity. So this is a simple movie here which shows you the budding of a pear-like vesicle into two spheres which are connected by a almost invisible neck. Now, what we have done recently, or more recently, let's say, in the last few years, is to look at giant vesicles that are exposed to a variety of external media or assays. So let me remind you that I'm talking about giant unilamellar vesicles. They have a size of about 5 to 50 micrometers. I mentioned the thickness is much smaller of the bilayer. And what we have found, depending on what we do to the vesicles, is that we see many different shapes, but all have some kind of necks. So this is a dumbbell, which means it's two spheres connected by a neck, pretty close to what I just showed you, but the difference is it's almost symmetrical, which means the two compartments have more or less the same size. So this is what I call a 1+1 sphere, because it consists of two spheres. Then we have here a long string or necklace of small spheres connected to a somewhat larger one. So this is a 1+14 sphere, which actually involves 14 necks. And then this is a long nanotube, or several maybe long nanotubes, which you cannot resolve optically because they have a width of about 100 nanometers. So we don't see from this picture what kind of shape these nanotubes actually have. Now, the same figures again, but with a slightly different emphasis. So because we have exposed these three GUVs to different external media, we can also view them at multi-responsive compartments. So in this case, we expose them to what you see here as a green background. This is cis-tag GFP. Here we have actually two simple sugars, sucrose inside the vesicle, glucose outside. And in this case, we have a compositional asymmetry, or a compositional sort of Q, which is GM1, glycolipids, which is embedded in the membrane. And this GM1 is a lipid which has a very bulky head group consisting of a couple of sugar groups. Now, just to emphasize the keywords again, we are talking here about necks and budding, and we can induce it by different external signals. Increase of GFP, this is this situation here. So you see here two different initial shapes, and when you increase the GFP concentration in the external solution, you see these buds forming. And here is a somewhat simpler case. You just do it by osmotic deflation, which means you take out volume out of the vesicle. And here you see also the time course. So this is within about 10 seconds, you see a transition from a pair to a two sphere or 1+1 sphere vesicle. Now, from a physical point of view, this is these necks are quite funny because you can think of them as wormholes in three-dimensional space. So this is a very narrow channel which connects these two compartments. And if you look at these shapes using the theory of curvature elasticity, you will find out that one crucial parameter which governs this budding or neck formation is actually spontaneous curvature. And so this is what I will tell you next. But before I do so, let me connect up to our current problem, which is corona, because when you look at the endocytosis of viruses, you have the same, one of the steps is precisely to form a membrane neck. So this is the cartoon. This is our virus in a very simplified manner. It has no, I mean, I omitted the lipid envelope and omitted the spike proteins. But this is basically a particle. It adheres, it is engulfed by the membrane, and after the engulfment, the membrane, the cell membrane actually forms a closed neck. And then, well, then there is typically some protein machinery in the cell which actually cleaves this neck, and you go to some release compartment which goes into the cell. And in fact, what we find from a theoretical point of view is that all of these different steps are governed by the interface of spontaneous curvature and something which we call the adhesion length. Okay, let me now tell you a bit about the spontaneous curvature. This is a key parameter which is intuitively quite obvious. The lipid bilayer has two leaflets. So let's say this is the inner leaflet, this is the outer leaflet. And the spontaneous curvature just tells you the asymmetry between these two leaflets. And well, this asymmetry can arise from many different molecular mechanisms. So this is indicated here. This was the case, these were actually the three cases I just showed you. This is binding of GFP to the outer leaflet. These are layers of two sugars, the smaller glucose outside and the larger sucrose inside. And this is an asymmetric mole fraction of GM1 in the outer or external leaflet. Now, I just want to summarize before I sort of show you separate or different examples that the spontaneous curvature is a fairly important quantity to understand what the membrane does. First of all, it bridges the gap between the molecular and the mesoscopic scale. It is also true that it is an important shape parameter because for a spatially uniform membrane, the shape of a GUV depends only on two geometric quantities, the volume and the area, and the spontaneous curvature. It's an emergent property in the sense that it is well defined on length scales which are a little bit larger than the bilayer thickness, so let's say 6 nanometer. And it's determined by the local bilayer symmetry. And for this reason, there are many possible mechanisms which can generate a spontaneous curvature. And here are a couple of examples. Now, here are some processes for which the spontaneous curvature plays an important role. As I will show you in some detail, is the size of membrane buds, the stability of the membrane decks is directly related to spontaneous curvature. Here's an example which I'm not going to discuss. So if you have domains which bud, domains which have been arisen from phase separation, you also have an important contribution or important impact of the spontaneous curvature. Spontaneous formation of membrane nanotubes is another example. Likewise, endocytosis of viruses and nanoparticles, wetting of membranes by droplets, and also, and last thing I will show you very briefly is active shape oscillations of GUVs. Now, in all these cases, there are two challenges. One is, how can you actually measure or deduce the spontaneous curvature, which are, by the way, called M. So this is a quantity which has a dimension 1 over a length. And what you would like to know, is it 1 over 100 nanometer, or is it 1 over 500 nanometer, or is it 1 over 1 micrometer? So how are we going to measure it? And then how are we going to specify and control the spontaneous curvature? Now, it turns out there is, we have developed a variety of methods to actually measure or deduce it. I'm not going to tell you the details about this. What I'm going to focus on in the next couple of slides is actually to specify how we want to control the spontaneous curvature. Let me first talk about stability of necks. So we have here the spontaneous curvature. Let's say a large spontaneous curvature would be 1 over a micron. Just mentioned that it can be positive or negative. This actually determines whether the bud goes outside or inside. So for the outbuds, we can directly conclude it's a positive value. We also know theoretically, if the positive spontaneous curvature goes above a certain threshold value, you get dumbbells with closed membrane necks. So as shown here, so this is actually an image, a confocal image, which shows a small sphere of radius R2 and a large sphere of radius R1. so a dumbbell or a 1+1 sphere. The two spheres have different radii, as indicated in the image R1 and R2. And these geometric quantities are used to define the neck curvature, which is just, excuse me, oh, what happened here? It's just defined by the mean of the inverse radii, which are the mean curvatures of the two spheres. So it's 1/2 times 1 over R1 plus 1 over R2. And this thing I call the mean, the neck curvature. And it turns out that this neck here, which is more or less closed, is actually stable if this neck curvature, which you can deduce geometrically just by looking at this image, if this neck curvature is between 0 and the spontaneous curvature. So what you get here, this stability relation is a local relation between the geometry and the material parameter. So the material parameter is M, and the neck curvature is a geometric parameter. Now, if you go one step further, you can actually determine the stability regime for these kind of dumbbells. So I've mentioned this before, I focus on uniform membranes, which means a uniform composition of the membranes, no domains or rafts. Then you can use the vesicle size as a basic length scale. And then you get from these three parameters I mentioned, volume, area, and spontaneous curvatures, you get actually two-dimensionless shape parameters, which is a volume to area ratio of V, which varies from 0 to 1, and the rescaled spontaneous curvature with the spontaneous curvature times this vesicle size. And this is what you see here. You see here a morphology diagram, which is at the x-axis is in fact this rescaled spontaneous curvature. This spontaneous curvature is scaled with the vesicle size, and the volume to area ratio V, which varies between 0 and 1. And the yellow regime here is in fact the stability regime in which such shape, which consists of two spheres, so 1+1 shapes, are actually stable. And one additional aspect, which is actually quite useful, but not so obvious, is that in all of these white regions here, if you would change V or would change M, the rescaled M, you would actually change the shape. While in this stability regime, if you increase M, the shape doesn't change. In other words, the shape here depends only on the volume to area ratio, but not of the rescaled spontaneous curvature. Now, the next point is controlled division of GUVs and something closely related, constriction forces. And so this is work by Jan Steinkühler, who actually is supposed to be in Chicago, but they closed the lab down, so he's back in Germany and waits till he can return to his lab in Chicago. Now, what he has done is he has used GFP, actually more precisely his tag GFP, which binds to certain types of lipids, NTA lipids. And I should say this cartoon is actually slightly misleading because the coverage, the density of the bound protein is much smaller than you would deduce from this cartoon. In fact, he uses nanomolar GFP concentration, which he can use as a simple control parameter. So he just adds his tag GFP to the external solution. And then he finds that the density, this density of bound GFP increases linearly with the solution concentration. And furthermore, by a rather detailed comparison between zero and experiment, he also finds that the spontaneous curve increases linearly with the coverage, as you would expect for a dilute regime. And thus, therefore, you can also deduce that it increases linearly with the solution concentration, which also means that just simply varying the solution concentration, you can in fact control the spontaneous curvature. And what I want to emphasize, because this is what is different compared to previous studies, is that it's really a dilute regime, which means that the separation of bound GFP is much larger than the lateral size of the GFP. That's what I just said. From this point of view, this is misleading a more realistic picture would be that we just have two, the two external ones and this one omitted. Now, this allows you, this control of the spontaneous curvature allows you to actually divide the GOV. And so what you do, you first deflate it. This is in fact what is going to happen here. You start with a sphere, you deflate it osmotically, and then you get a dumbbell. And then we are, if I just go back to this diagram, we are somewhere here on this line. Here we have a dumbbell. And now we know that the shape is not going to change if we go here, right? And this is what I explained here. But if we now increase the spontaneous curvature even more by adding more external GFP, what you actually see is that the dumbbell is cleaved, I mean the neck is cleaved, and the dumbbell is broken up into two daughter vesicles. And this is also shown here as a small movie. So you see here after now you give the more GFP, which increases spontaneous curvature, and then it's separated. And in fact, you can, when you follow it, you see that both of these vesicles undergo normal diffusion. There is nothing like a tether in between, which you might suspect perhaps. The whole thing was actually 8 minutes. Now, from a theoretical point of view, this was very nice because it happens that I was thinking about this regime, and what one finds theoretically is that the spontaneous curvature in this regime, in this yellow stability regime, generates a constriction force. So this is in this cartoon here. So you have a force which radially acts on the neck. And this force is simply 8 pi times kappa. I may not have mentioned kappa. Kappa is the bending rigidity. Well, actually it's written here. And so this is of the order of 20 kT typically. And then you have a term which is the spontaneous curvature minus the neck curvature. So at this line, this term is actually vanishing. So the force is 0, but as you go inside, m becomes larger than this. And then you generate a force which increases linearly, more or less, with the spontaneous curvature. So this is shown here. This is actually as a function of the curvature difference, m minus m neck. And you see the constriction force in piconewton. And this is just a linear dependence, as shown here. And you can also see here 3 examples of potting machineries, dynamine, escort, and FISZ, which FTSZ, which are actually protein machineries which are used in vivo. Okay, so far I've been talking about just 2 spheres. Let me tell you that you can have much more complex shapes which consist of many spheres. So all of the shapes that I show you in this cartoon, first of all, they are formed by a single membrane, and pairs of neighboring spheres are connected by membrane necks. So I've just sort of drawn all possible spheres here, or multi-spheres here, which consist of up to 4 spheres. One of the things which you learn from the theory is that only 2 radii are possible. So if you have large spheres which have radius RL, and you have small spheres with radius RS. And so in general, you have a certain number NL of large spheres and a certain number NS of small spheres. So in this example, the total number of spheres was up to 4. And I should say that in this cartoon, all of these shapes have actually the same membrane area. So if you could just go from one to the other in principle, again, by changing the volume. If you look in more detail, you find that the stability regimes, you have for all of these shapes, certain stability regimes and a certain overlap with these regimes. Now, this is just an example for the experimental shapes which you see, multispheres which you see experimentally. So in this case, just 1 large and a couple of small spheres and small spheres. And you see that there are, these are 4 small ones, these are 5, 6, and so on and so forth. You also see that the small ones can form branched rather than linear chains of small spheres. And this is actually what I showed you in the very beginning. This is a 1 + 14 sphere. And well, the number of necks in this case is just the number of small spheres. And if you have a more general shape, you have a certain number of necks, which is the same total number minus 1. And one thing which was surprising in the experiments is that it's actually quite mobile. So if you would look one of these little spheres here, for instance, look at them, watch them, you will find that they might actually move along the other small spheres, and they could go from a branched, for instance, to a linear chain. Now, this is a particular large linear chain, a particular long chain, which has actually 39 equal chains, equal small spheres. And this is already obviously something that you could call a nanotube, even so it's still optically resolvable. And this would bring me to another thing, which I'm not going to tell you in any detail, but just to mention that we have seen various examples of nanotubes. You can understand them in terms of what we call the spontaneous tension. In fact, you find theoretically that the total tension in the membrane can be decomposed into a stress or mechanical tension and a spontaneous tension. This thing is just 2 kappa m squared, which is a material parameter, while this is a complex quantity. And well, what you can conclude in general, whenever you see tubes like this, you can say that the stress or mechanical tension is actually quite small compared to the spontaneous tension. So the spontaneous tension dominates. I'm going to skip this, but I just want to tell you this thing here, because this is a very practical aspect of nanotubes. You know, presumably, that conventional UVs rupture rather easily under osmotic inflation, trunk adhesion, micropipette aspiration. And what the membrane nanotubes do, they provide an air reservoir, which means that tubulated UVs have a very low mechanical tension or stress, and they do not rupture under these strong mechanical perturbations. Okay, one point about the tension. The elastic stress about which I'm talking about is actually not a material parameter. It depends on the shape. It's a shape-dependent tension. And because of this reason, it actually provides certain headaches. And it's also a good motivation to look into simulations where you can measure it in some detail. And one insight which we got recently from simulations is that you should distinguish bilayer versus leaflet tensions, as shown here. And these leaflet tension govern also the shape of nanovesicles, as shown in this figure here. Now let me see, I have 2 minutes according to my handy. So this is budding of a nanovesicle. This is again a neck. And well, outlook on related processes. I will not tell you about any details about this. What I haven't talked about yet is about wetting of membranes, which is a very interesting subject, but sort of slightly neglected by the community. And let me finish with shape oscillation. This is originally an experiment from the Schwille lab, Petra Schwille. This is what they have observed. And in fact, you can understand this in terms of the oscillations of bound min proteins. And if you go to a slightly larger scale, you would say, okay, we have here an oscillation of the spontaneous curvature. And if you do this in quantitative terms, you find that the neck curvature, as shown here, actually has an oscillation like this. This is about a minute and one oscillation. And well, it's a more or less quantitative explanation of this interesting observation. There is even something else. What could you do with these kind of compartments? You could use them as delivery systems. We could also use them to store and deliver nanoparticles, for instance. These are all simple ideas which haven't really been tried so far. And these are my co-workers at our Max Planck Institute. And here is also a number of collaborators with which we have done this work. So thank you for your attention. And you're welcome to ask questions if you manage to do so. Thank you.
So thank you very much, Dr. Lepowski, for a wonderful presentation. We have a number of questions that have come up, so I'll go ahead and start those, and please feel free to ask additional questions as we go along. So the first question is, do lipids diffuse from one sphere to the other in dumbbells?
Yeah, that's a good question. And we haven't started this in detail, but that's what you would expect, because it's, as I emphasized, can you hear me? It's actually one membrane, right? It's you can, you know, if you look at this deflation, for instance, you can see that it's originally, let's look at this here. You see it's one lipid bilayer, which forms this prolate-like shape. And then you just take out volume, which means you deflate it osmotically. You take out volume and you go to this. And of course, the neck will form a certain barrier because microscopically speaking, it's now of the order of the thickness, the neck, I mean the radius of the neck. So there is a bottleneck in the direct sense of the word, because of course you have, if you want to bring a lipid from here to here, you have to cross this barrier. But otherwise there is normal diffusion, because these membranes are still fluid. I mean, the temperature is constant.
Thank you very much. The next question is, by which mechanism does GFP binding to the membrane induce membrane curvature? Yeah,
this is a good point. If you think about a mechanism, what is a molecular mechanism? In fact, what we have emphasized in the paper is that the spontaneous curvature induced by this dilute coverage is surprisingly large. And so if you look at a variety of mechanisms which you would say are the standard ones, you know, you would have some loss of entropy because this thing is a rod-like molecule and it cannot sort of, it would like to bend the membrane in order to explore more space. Or you can think about various other mechanisms which have been discussed in the literature. You find out that a single one is not able to actually generate this large spontaneous curvature. So I haven't, I had a picture of this, right? So this is actually what you measure. So you get this range of forces, which means that the spontaneous curvature are in a corresponding range, which is sort of relatively large. So to make it short, we don't know at the moment precisely what the molecular mechanism would be, but the whole sort of study is in this sense generic, because it just says, you know, we have a spontaneous curvature, which we can measure by a direct comparison of experiment and theory. And when we take this value, we get certain forces, and this is in agreement with what we see, that these forces eventually, so what is shown here, once this curvature difference exceeds this sort of threshold value of about 6 per micron, which is in about 1/150 nanometers, you would get fission.
Thank you. So the next question is, in multispheres, could you please comment on the reason behind the possibility of only 2 radii?
Yeah, this is another good question. This is actually a consequence of what we call the shape equation. So if you look at the theory of curvature elasticity, and in particular the spontaneous curvature model, which goes back to Helfrich, you can look at the shapes of minimal energy or extreme or locally minimal energy, and to get a certain equation for the curvature, as a Gaussian curvature, the mean curvature, Gaussian curvature, and also a complicated term, which is a Laplace-Beltrami operator. But if you assume that you have spheres, as in the experimental observations, this shape equation actually simplifies and becomes a quadratic equation in the mean curvature. So if you think about any of these spheres and you think, okay, we have now spheres, and we look at the shape equation, we actually find we can only have two solutions because this equation is quadratic in the mean curvatures. And so these two radii, which are the inverse curvature for out spheres at least, apart, otherwise they would have to think about a sign. These two radii are just the two solutions of this shape equation. And in fact, this is something which is pretty simple, and it's also robust because this is precisely what you see in the experiment, right? You always see a certain number, in this case it's just one large sphere and a certain number of small spheres. We also have examples where you have several large ones and several small ones. And then there is this general case where you actually have equally sized spheres, which means spheres that have all the same radius. Let me just go back to this diagram here. You see, this is actually the limit here. So at this limit, we have two spheres of equal size. And this is a general aspect. So all these multispheres have a stability regime like this, and they all have an upper line, not an upper, lower line in the term of volume, where you would have all spheres would have the same size. Here we just have two spheres, so we just have two spheres of equal size. But if we have n spheres, NL plus NS, we would have then n spheres of equal size.
So I actually had the same question, and as a follow-on, if I could ask if there are additional control parameters that you know or might be hidden and would have to be elucidated that would expand the space of possibilities of the number of radii that would be allowed and thus controlled in order to make different types of structures.
Yeah, that's a good point. I mean, from a theoretical point, it's simple. You just have to take domains. So you would not take a uniform membrane. I mean, I've always talked here about the simplest case, assuming that the composition of the membrane is uniform, laterally uniform, and so also the elastic curvature parameters are laterally uniform. As soon as you have domains, you can have more than two radii. So if you have two types of lipid phases in the vesicle, you could have up to 4 different radii in principle. But this is something, I mean, I would like to see experiments on this, but this is a challenge.
Okay, thank you. So the next question is the person with the query says, I might have missed this, but are the lumen of the multispheres interconnected?
Yeah, this is in a sense again clear from the history, right? But of course, this is another thing one might try to do quantitatively. I mean, if you look at this time evolution, right? I mean, this is one lumen, and then this neck closes. But I mean, a strong point is you can always go the other way. So if you just, if in this case, this osmotic deflation, this is not so difficult. You just inflate it now. You start from this, inflate it, and then you go back. So you open up the neck. This is in fact an interesting question that we have pursued in various ways, because when you close, and if you had an ability to do this systematically and in a controlled manner, you could, for instance, have some chemicals or some particles in one compartment and another one here, and then you open it up, and then the mix and things like that, right? But in general, it is true that the lumen is connected. Of course, it's again a very small connection, so it would make some sense to actually measure this, but it's something we haven't done.
So the next question is, what are your expectations of the effects from encapsulated system inside the GUV, like cytoskeletal proteins or other encapsulated biomaterials, to the SP curvature, or your theories with membrane necks or membrane tension for vesicle separations?
Well, this is a hard question in a sense. From my point of view, I would try to separate the membrane from the cytoskeleton and use the cytoskeleton or the maybe synthetic cytoskeleton as a source or an origin of forces acting on the membrane, right? I mean, we know from the biological, from the cellular membranes, that whenever there is something which grows or which shrinks, it can exert forces onto the membrane, and then the membrane responds with certain deformations. So this would be another step in the sense that you would now have not only spontaneous curvature, but you would have local forces. I mean, if you think again about this thing here, if I have, this is of course now, there is no scale I see, but this is maybe 10 micrometer in size. This thing is actually only 4 nanometers. Let's say an actin filament has 8 nanometers. This would make, presumably, if it grows or shrinks here, it makes a local perturbation. And I mean, this has also started to some extent experimentally. There are, I think, Lieb-Chabert, there were some experiment already in the 90s. But again, this is something we haven't studied experimentally. Theoretically, it wouldn't be so difficult to make some predictions about this. But I would not want to sort of view it as a part of the spontaneous curvature. I would view it as an external force acting on the membrane.
Thank you. So we have time for a couple more questions. For the dividing vesicle, how did you add GFP? Is the GFP homogeneously distributed, or are there some sort of gradients, for example, due to, it says fusing from one side in solution or in the membrane?
Yeah, this is also a good point. I mean, I didn't talk about this, but technically what has been done is to use what one might call dead-end microfluidic channels. So these are microfluidic channels which are dead ends, and they are directly connected to the main channel, but they are not directly exposed to the hydrodynamic flow. So the exchange of the main channel with the dead end channel is by diffusion. And this has a big advantage that you don't deform the vesicle or perturb the vesicle by the hydrodynamic flow. I mean, as you presumably know, if you have some flow, the vesicle would also try to adapt to this flow. So these things are, I don't have a, maybe I actually stop this. Now this might take too long. I mean, this is basically a dead end, which is a couple of maybe 20, 30 micrometers long. And you can see that when you add in the main channel, you add GFP, you see how it spreads by diffusion into the dead end channel. And then you also can be sure that it's only what you see in terms of shape transformations or shape changes is only induced by the GFP rather than some flow.
So the next question is, can all these membrane properties be explained by treating the membrane as a viscous fluid?
Well, I must say this is a complication that I've refrained from working on, because viscoelasticity is, of course, a very large area which easily introduces a variety of parameters. So what the nice thing about, from a theoretical point of view, about all of these shape changes I've been talking about is that you can explain and understand them in terms of a few parameters, right? I mean, basically you have, the shape is 2 parameters, 2-dimensional parameters. If you add domains, you get a certain larger number. If you want to look at viscoelasticity, you look at dynamics as dissipation, and then things become slightly complicated. So I have, apart from the last example where you have this kind of quasi-equilibrium, even though it's out of equilibrium by ATP, I haven't really thought carefully about viscoelasticity, but there are many attempts in this direction. I mean, I know that people have studied the dynamics of beads, for instance, and try to see to what extent what is called the two-dimensional viscosity might be dominant, the three-dimensional one. So if you have a little particle which sits on the bilayer membrane, on the vesicle, you have, of course, to some extent, just the usual viscosity from hydrodynamic drag in the surrounding medium, but you also have the viscosity in the internally in the membrane. And there is a long discussion about the relative importance of these two things. So to make it short, I'm not an expert on viscoelasticity.
Well, thank you very much for a wonderful presentation and a very interesting Q&A following. There are quite a few more questions, so unfortunately, we're going to have to leave it here and move on to the next presentation, which is by Dr. Karen Jacobs. So thank you again, Dr. Lepowski, and I know there's going to be some follow-up to try to have some of the outstanding questions answered offline.
Okay.
So thank you again.
Bye-bye.
So it's now my great pleasure to introduce Dr. Karen Jacobs for the next presentation. Dr. Jacobs is a German physicist and a professor at the Saarland University. Jacobs studied physics at the University of Konstanz and received her doctorate from the very same university. Since 2004, she's a fellow of the Leibniz Institute for New Materials. Her research focuses on microfluidics, bioadhesion, and functional materials. Jacobs is a member of the Akademie der Wissenschaften und der Literatur. She gave the Beller Lecture of the American Physical Society in 2015. And since 2016, she is a member of the German Council of Science and Humanities. Karen does research in condensed matter physics, biophysics, and nanotechnology. Her tutorial today is titled Unspecific Interactions in or of Cell-like Compartments, Theory and Experiments. Welcome, Dr. Jacobs, and we're looking forward to your tutorial. I think you're still muted.
Thank you. You have unmuted me. Thank you for the kind introduction. I was actually prepared to give also a hands-on workshop in Santa Fe, so I'll keep this stuff for next time. And the tutorial is really meant for students, for young PhD students and so on. So I'd like to talk about the unspecific interactions of in or of cell-like compartments, some theory, some experiment. That's my team in Corona times. We never managed to get all of them at once in line, but never mind. We're already taking shares in the lab, so things come back to normal quite a bit. All right, now this doesn't want, next. Unspecific interactions determine, for instance, the shape of cells or compartments. So, and also the elasticity of cells on compartments. So all what Reinhard was talking about before, actually you can draw back of some interaction that is due to intermolecular forces, due to bond repulsion, due to steric hindrance whatsoever. So there's a long list of things where they are determining what actually is going to happen. So I can't go through all of them, but I'd concentrate a bit of the adhesion of something to a wall, to a substrate, or proteins that stick to other proteins. So coming back to the basic physics, there are four fundamental forces, the strong and the weak force, but they are about the stability of protons, neutrons in the nucleus. So they're not so important for us. Well, all is stable. then for sure there is gravity. But for our systems, we can usually neglect gravity because these intermolecular forces are much larger. And the intermolecular forces are actually electrodynamic forces that comprise the electrostatic forces like Coulomb forces and also permanent or induced dipole-dipole interaction. And they're subsumized, they have different names, these forces. In the following, I'll call them intermolecular forces, but they're also called London dispersion forces. And there's some mixing up of keywords here, but let's stick for intermolecular forces for the remainder. Following a list of Jacob Israel-Lachwili's textbook, there are capillary forces, contact forces, and so on. So the capillary force usually is attractive and is due to a water layer, or if you have different liquids, you can also have an oil neck or whatever. Contact force is actually of quantum mechanical origin, but usually it's also named here in the list of intermolecular forces. So it's about the core electrons, where one electron is living, another one can't be in the same quantum numbers. The range is typically of very short distance. So we're talking about 1 nanometer here. And then for sure, electrostatic and electrodynamic forces, Coulomb interactions, screened or non-screened, there are charges or ions involved. And my guess is you're pretty much familiar with that one. And then there are van der Waals forces. This is about the interactions between permanent and or induced dipoles. They are always present, so they cannot be screened. They are attractive and they are due to the outer electrons. Their range can be of long distance. Then there are depletion forces, for instance, in a solution of large and small particles or molecules. Also hydrophobic forces, there we have depletion forces due to water network of hydrogen bridges. And there are hydrogen and sulfur bridges, but usually they are more regarded as bonds. But still they're very important. So details you'll find in good textbooks like the Persian, the Van Os, or the Jacob Israel-Lachwili's books. And or you just apply to the Matter of Life graduate school and take the physical chemistry for life in the first semester. Details about the course will be given by Michael Grunze in the next talk. So there are way too many forces to talk all about, so we have to pick a few. Do they also play a role in everyday life? Yes, indeed they do. For instance, they determine the repose angle of sand or flour. They are responsible that the Xerox machine works. They determine the stability of coatings, the activity of soap or tensides, the stability of foams, the effectivity of lubricants, the stability of solutions that contain small particles or colloids, like in paint, milk, nanoparticles, or DNA solutions. And then they also determine the action of adhesive tape. They make the gecko climb, and also to the adhesion of bacteria to our fingers, to door handles, cells to something else, viruses to something. So let's pick an example. Let's take a bacterium, a small object, or an artificial cell. Now, there are forces due to unspecific interactions, and there are a few that have been listed before, like the screened electrostatic interactions. Here, bacterium, a small object close to a substratum. Van der Waals interactions with a substrate, and short range, like the hydrophobic interactions. Also, steric hindrance is due to the repulsion of the electronic status that one electron here has cannot interfere with an electron of the substratum with the same quantum number, and therefore we get this repulsion. The same is true if you have some other molecules on the surface. So two hedgehogs cannot come closer together because of their fur. And then there are specific interactions, forces due to specific interactions, like ligand-receptor interactions, ligand-mediated interactions, or, as named before, the hydrogen or sulfur bridges. But these are not subject of this lecture. Now, let's pick a very simple example. Let's cross out the electrostatic interaction because most of you will be familiar with that one. So we just disregard them. They're still there in our systems as well, but if we hold them constant, nothing will happen, and we can concentrate on these two ones, the van der Waals forces and the short-range hydrophobic interactions. Please keep in mind that van der Waals interactions are sensitive to the geometry of the interacting object. So if you have, for instance, two atoms interacting, then the interaction potential is proportional to 1 over the distance to the power of 6. And this is why people usually say, oh, well, van der Waals forces are weak and are short distance. But most of the systems in our daily life or in the lab are more like sphere surface interaction. And there the interaction energy goes like 1 over the distance between the two objects. So this is more like a Coulombic force. So it can be of long range and it can be quite strong. So in the following, we'll have the geometry of a sphere of radius r near a flat surface, or we have two flat surfaces interacting with each other. And there we get a distance relation with 1 over distance squared. So let's start here and look at this simple situation. There's a particle near a wall at a distance h. And the question is, will it absorb? In this example, as I said before, no charges shall be involved, or at least they don't change while we're looking at the system. And the van der Waals interaction should be the geometry of two planar semispaces. So what will the potential be looking like? Well, there is the Born repulsion, and a usual approximation is a 1 over distance to the power of 8 with a certain proportionality constant. And then there is the van der Waals potential with the Hamaker coefficient here and the 1 over distance to the squared relation. The Hamaker coefficient depends on the index of refraction and of the dielectric properties of the involved materials. And here there are, well, basically 3 materials if you watch this as a homogeneous object, the medium and the substrate. So the sum of potential of the potentials gives here this effective interface potential, the black curve. It looks like a Lennard-Jones potential, yet for the Lennard-Jones potential, this is has different exponents because it describes the interaction of point-like objects, which we don't have here. So this is a very simple potential. Now the question is, will it absorb? Yes, it will absorb because we do have a global minimum of the potential for all the distances. So wherever we start as a distance, or here is the distance as a function of the potential, here is it is attractive, negative potential, here it's repulsive, a positive potential. So wherever we start, we find that the gradient of the potential, which is the force, will make the system slide into the global minimum. So yes, it will absorb. But what happens actually if we have a stratified wall, for instance, a silicon wafer with a silicon oxide layer on top? So most of the substrates we use are not completely homogeneous, but they have somehow a different surface composition. Now we need to change here the van der Waals potential. The short range potential stays the same. If we had before, for instance, only, let's say this is silicon dioxide. If we had silicon dioxide before, the short range force should not change. But the long range van der Waals part will change because we have the interaction of this object with the light blue layer and the interaction of the object with the gray layer. If it's the silicon, for instance, this is semiconducting and this is more like a ceramic. And depending on this thickness, we'll get different types of long range van der Waals potentials here. So they can make up for a hump in the positive, in the repulsive part of the potential. Now the question again, will it absorb? Now that's the question now, where is the protein or the object when you start? Do you have a strong flow that possibly pushes the protein to the wall? Or is it far away from the wall and then it will see just the local minimum at long distances? But if it's close, it will feel the global minimum here. So it's not clear yet. It depends on your experimental conditions. So, and this gets even more complex if the Coulomb forces are present, which we just need to add here, however they look like. And you have seen very likely potentials that have small shallow dimples here, and then another dimple, maybe go positive again or whatever. So you can construct really, really weird potentials, and it's always the question, which minimum will the object see? In other words, we can change, we can really tune the interaction potential. For instance, if we take a substrate that is stratified and modify the surface layer in thickness, and we're talking about here between 1 and, well, above 70, 80 nanometers of silicon dioxide, it all reacts the same. It doesn't matter if we have 70 nanometers or 700 nanometers. We change this part of the effective interface potential. If we now change something on the up layer to the outer layer that comes really into contact with our cell, with our protein or whatever, and change this chemical composition, for instance, from a hydrophilic silicon oxide to a hydrophobic CH3 end group, then we change dramatically the short range forces. And you can see that easily because a water droplet changes from the hydrophilic situation where it's a flat pancake to the hydrophobic situation where you have contact angles way above 90 degrees. So with this simple trick, we can probe which forces are present or are dominating our system. And the depth of the global minimum is very often, it is now depends on your system, a very important value to know. For instance, it characterizes the adhesion force of a bacterium to a surface, or it characterizes the contact angle of a liquid on a surface. Now we can go on and test, take some probe, like the polymer, a protein, bacteria, a cell, or a gecko paw, and check in which situation we get, for instance, which adhesive force. Now let's have a look at proteins. Now we go to another geometric sample situation, namely a sphere on a flat surface. So we expect a 1/r dependence of the potential. However, the situation here, for instance, is first, I assume the protein to be somehow a sphere, round, which is not really true, but it's a first approximation. Here, we assume it to be 4 nanometers, and we have 4 involved media. So the protein, the medium, typically water, for instance, again, the silicon dioxide and the silicon. This means we need 2 Hamaker constants. This one here, characterizing the van der Waals interactions of the protein with a surface layer, and a second summand for characterizing the van der Waals interactions between the protein and the subsurface layer, which is the semiconducting silicon. These Hamaker coefficients can be calculated using the dielectric properties of the involved materials, like the dielectric constants and the refractive indices. Now, what if the silicon dioxide layer varies? Let's have a look for 2 different thicknesses. So here is the distance r that the protein is hanging around above the surface. Let's say here up to 4 nanometers. Here is the substrate. And that's the van der Waals potential measured in kBt units. So here's -1. And we'll see only adsorption if the attractive van der Waals potential, you see it's attractive, it's minus, is larger than thermal fluctuations, which are of the order of kT. So this means below, if the curve is below here around, then we expect adsorption. And you see, if we are on the thick silicon oxide, when do we face attractive forces below 1 kBt? Well, we have to come close to the surface, roughly 0.5 nanometers, which is pretty close. However, if we have only a thin silicon oxide, you see already 2.5 nanometers from the surface, the protein feels the attractiveness of the substrate and will absorb. A huge difference, yet chemically, it's absolutely identical. We can show this. So we face a stronger adsorption on this thin silicon dioxide layer. And why? Well, there are stronger van der Waals interaction with a semiconducting silicon than with an insulating SiO2 surface. And you can find it here for the dielectric properties that go into the Hamaker coefficient. The situation holds also true, even if we add the always present Coulomb interactions. We just have to make sure that when we do the experiments, we do it all in the same buffer solution or whatsoever. In the experiment, stronger adsorption can mean that the film thickness is affected, or the density of the protein film, or the size of an adsorbed protein molecule. So it can be just, if there's a strong attraction, possibly the molecule deforms and lies flat on the surface. In this simple continuum mechanical approach, these type of specialties are not included. It just tells you, okay, the attractive force is stronger on this part and lower on that part. Now, what can you do? How can you influence the intermolecular forces? How can you find out which forces is actually dominating or hindering what you would like to have in your system? So if you are facing problems due to a capillary force, just go and immerse the system into fluid. So people doing force distance curves of a small object with an AFM in air often have trouble with the capillary force. If you immerse the entire system in buffer solution, all is fine. Exchange the fluid if you can from water to oil, change or control the air humidity. For the bond repulsion, try to change the chemical composition of the last atomic layers and see if this makes a big difference. For the electrostatic and dynamic forces, you add or remove charges, vary the ionic strength, change the pH, change the buffer. This is all known. For the van der Waals forces, try to vary the thickness of a stratified system. Keep the chemistry and vary the geometry if possible. And this is also for the theoretical physicists and amongst us. The van der Waals forces are often neglected, because people think they are just 1 over r to the power of 6, and they are away. Yet, even the gecko feels the subsurface composition, and this gecko weighs about 100 grams. About depletion forces, try to add or to remove dissolved smaller particles or molecules in the system. And for hydrophobic forces, if they are facing these types of problems, change the wettability of the interacting objects, for instance, by adding proteins like hydrophobins, I will be talking about next, or coat the surface with any type of thin layer. So, techniques to determine intermolecular forces. You can measure forces directly, for instance, by peeling off a scotch tape. That's what the 3M, for instance, does. Lifting a colloid, lifting a cell, and you can measure the force either by optical tweezers or by force sensing system of an atomic force microscope. Yet there are also many indirect techniques. So determining the force by determining the contact angles with a goniometer, for instance, and check the contact angle, or determine the film thickness with an ellipsometry or by capacitance measurements, measure the bending rigidity, measure if you use the AFM and push on a membrane to find out what the rigidity is. You can measure the micellar particle concentration to find out what the cohesion and repulsive forces are. So there are really, really many techniques. And I'll show you just a few. And here are intermolecular forces at self-assembly. It's here a very nice publication of Steve Granick what small particles can actually do. And the interplay forces is acting here between molecules within the layer, between bilayer or multi-layer sheets, within the liquid, with the the components with the liquid medium. And the question is, which forces are dominant? And for instance, if I like to achieve a compartment like that, which ingredients shall I take? So which forces to change to achieve the desired result is the biggest question. Now, I'll show you next an example of a special protein that is self-assembling. And the special protein is a so-called hydrophobine. It's a part of a filamentous fungi, and it's very amphiphilic. So here is a hydrophilic part in blue. There are some charges, and here's a hydrophobic part in red. So whenever we bring them in a microfluidic surrounding like this one, where we have aqueous finger phase, which we push with a pump, and here, which is not shown here, is the continuous phase like oil or hexadecane. Now let's add the hydrophobins, and they immediately go to all the interfaces, not necessarily only to the oil-water interface, but also to the oil PDMS interface of the channel and whatever. So, but now if we push and look from above, these two fingers don't coalesce, but they go together, they zip together. We can unzip them. But if we go on, we can form a hydrophobin bilayer. And how we kind of proved that is indeed a bilayer, you can find the details in this article here. What I want to share with you is the techniques, what we can find out by just watching here the meniscus, for instance. We can measure the bilayer tension. We can determine the bilayer tension by measuring here the contact angle between these two fingers. It's that one. We can calculate the adhesion energy by watching this, measuring this angle there. And by introducing electrodes in this finger and another one in that finger, we can measure the capacitance through this membrane and can deduce the bilayer thickness by comparing with other systems. For instance, if we have, instead of oil phase, we can have air and exchange then the media. Maybe you have already realized here we have reversed the situation. So the continuous phase is buffer and the finger phase is oil. And so we get, as compared to this bilayer here, an oppositely oriented bilayer. So here we have the hydrophobic parts of this protein looking to the outside and the hydrophilic parts inside. Now the question is, when do we get a really, really stable bilayer? And the cool thing about the hydrophobins is the molecules can be modified by genetic engineering to possess different properties. For instance, different charges. Here are the different types of proteins that can be produced. This is with a collaboration with Finland and Markus Lienemann. And by doing so, and the experiments I've shown before, we can determine the bilayer adhesion depending on what type of molecule we use. For instance, if we reduce the charges, we get just a slight increase in the bilayer adhesion, but increasing the ionic strength, then we get a strong bilayer adhesion, if we like that. So find the best molecule for a stable bilayer. Now, what can we do? This is now the stable bilayer. Now we can jet a liquid push it to a budding, like a budding vesicle, but this is really pushed. You see the video here, and this is now a really giant vesicle. You see here the scale, it's 100 micron. We can also produce much smaller ones, but this was the first we did that was stable. And as I said before, it can also be reversed so that we have a hydrophobic part on the outside, a hydrophobic pocket in the inside, and hydrophilic things can be transported in a hydrophobic surrounding, or the other way around. In a hydrophilic surrounding, we can transport here in the middle layer something hydrophobic. But what we also can do, we can insert a gramicidin A and get a functional ion channel. So we can, this is kind of a little compartment. We need still to infer the stability, possibly it can pass the stomach, so we can use it as a drug taxi. But the question here is there a direct measurement of the interaction forces? I've shown you now some indirect measurements, and yes, there are also techniques that are kind of direct. And in the remaining few minutes, I'll show you what we do using an AFM cantilever. Remove the normal tip, attach a bacterial cell or some group of cells, and then we do force distance measurement. So we press the bacterium to a surface and measure the kind of de-adhesion force that we need to take the bacterium off the surface. And this is defined as adhesion force. Now we take again our silicon oxide wafer sets, the one with the thick and the thin silicon oxide layer, and the same pair of silicon wafers, but with a hydrophobic self-assembled monolayers on top. So hydrophilic is blue, and you see here is the occurrence of a certain adhesion force in nanonewton. And for the thick silicon oxide layer, we get about 0.3 nanonewtons for the mean of the Gaussian. But if we have only the thin silicon oxide layer, it's more. It's nearly double the force that we had before. For the hydrophobic system, it's a similar situation. Also here, we have a stronger adhesion, bacterial adhesion on the thin silicon oxide layer. And the reason is the same as I said before for the single proteins, that interacting with the semiconducting silicon is a stronger attractive, giving a stronger attractive van der Waals force than if there are this ceramic-like silicon dioxide layer. What does it mean? Indeed, van der Waals interactions are important for bacterial adhesion. So if you really want to control the force, you have to know how the system is built up in detail. Yet here, if you look at the overall force scale here, it goes from 0 to 1 nanonewton, and here it goes from 0 to 10 nanonewton. This means the particle, the Staphylococcus we're looking here, is holding much stronger to a hydrophobic surface than a hydrophilic surface. This is true for many of these bacteria. So here, the chemical composition of the surface is actually the leading force, or the short range force is the leading force for that system. Yeah, so what? Take home message for testing adhesion, the effect of fluoride containing mouthwash. We found out if we just detach strep mutans or strep oralis, both are active in our mouth. If we put them in a fluoride containing mouthwash or toothpaste, as you can buy it in the drugstore, we see that only the adhesion force is only half of the force that it was before. So even if you apply only for 3 minutes, this is already in saturation. So in silico, in our lab, we find that the adhesion force is reduced to 50%. And in vivo, there are studies since the 1920s or so that you get, if you apply fluoride toothpaste mouthwash, a huge reduction of carious lesions. Conclusions: intermolecular forces are many and multifold, unavoidable, easy to change, but also easy to change unintentionally, yet very hard to control. So I close with keep calm and try hard, which is actually true for our situation now as well. And I'd like to thank the organizers for going virtual and for putting this together. Looking forward to the in-person meeting next year. I'd like to thank my team, who nearly all of them contributed somehow to this talk, and to all the collaborators I have listed there, the funding agencies, and we're looking forward to our new building, which you see in the middle, that is hopefully not affected now by this virus, the Center for Biophysics at Saarland University. Thank you for your attention.
Thank you so much, Dr. Jacobs, for a very nice presentation. We have time for some questions, so we will go ahead and jump right in. The first question is, can you model how increasing concentration of protein affects the probability of adsorption?
Yes, definitely it does. It does. So I don't do the modeling, but the collaborators of us, Ludger Sanden, for instance, does it. Yet, at the moment, we are not looking at overcrowded situations, but rather at situations where we just are not running out of protein. Let's put it that way.
Okay, thank you. The next question is, could you talk about the forces that are present in protein-cell, protein-protein, or cell-cell interactions in water, and why these unspecific interactions are not large enough to induce unspecific adsorption of these components?
Well, this is a question for a PhD to answer, right? I mean, it depends what type of protein, what type of cell, in which surrounding. I hope that it somehow became clear that just by naming a few things that are interacting, you can't say anything about the strength. You can't say anything about the system if you don't know a lot of details about the system. So if the question is, can you talk about the forces? I say, well, all of them can be candidates that are important, and we have to talk to each other now, which ones we might be able to exclude from scratch and which one we might have to look at. So talking about the system, first, I would try and change the buffer solution. Is the buffer influencing the outcome of the experiment? If yes, then I have to think what thing of the buffer is actually the problem. Sometimes you have a dirty buffer solution, then it's not the buffer itself, but it's the particles that are inside or the molecules that are inside. So if you just formulate the answer like that, it is a huge field to answer.
Okay, fair enough. The next question is, could a flat but porous and flexible surface adsorb better than a flat and smooth surface to another flat surface, all other things than physical structure being equal?
Oh, yes, this is a very nice question. Thank you for that one. Yes, it is really, really important. And talking about curvatures, like Reinhard Lipovsky before, you need to look at the curvature of this surface. If it's flat, then it's kind of a very theoretical situation. You don't have to care. You just take the distance between your object and the surface. But if it's bent, you need to take into account that possibly not the direct connection of the surfaces is the closest, but possibly there's a little spike next to it. And then, for instance, for bacteria, we could show that there is an optimum roughness where bacterial adhesion is the lowest. So the strength is very, very weak. But if you increase the roughness so that the bacterium can lie on a rough surface, like in a cushion, then adhesion is the strongest. So it's very much depending of the surface. So if you have a porous surface, the question is, how large are the pores? If the pores are in the order of the diameter of the object, I would say you will have a large effect. If the pores are very small compared to your system size, then possibly the pores and even the distribution of the pores doesn't have an effect. But it also depends on what is in the pores. Is it covered with water? Is it filled with water? Is it filled with oil? So do you have then a wettability change just by the filled pores? And how about the roughness of the pore surrounding? This is really a huge field, and we have just tested it for it's in Nano, published last year. Where we find the optimum roughness for non-absorption of proteins, bacteria.
As a quick follow-up, does the modeling look at moments of the shape distribution, for example, in trying to assess the roughness?
I'm not sure. Can you pose the question again? Which is the roughness of what?
The roughness of the adsorbing molecule, or the adsorbing protein.
Ah, okay. Well, if you're asking about that one, that's more a question for people who can do kind of atomistic simulations, right? So all I've been talking about in our potentials was a continuum mechanical approach. But in our systems, we have seen that, for instance, the protein can undergo changes. And if you take amylase, for instance, it will change with changing pH. So this is a very important question. But things get then really complicated. And if you ask the theorists, they don't like these wobbly proteins that change the shape all at once, because you need a lot of calculation of computer power to do it. But yes, this is important, and there are people who are on this track. And but we are far away from our experimental situation to come that far. What we can do is we can look at for instance, by neutron scattering, we see the density of protein films. And if we have only few molecules absorbing on the surface, we can nicely see that the density of the film is affected, for instance, through this different subsurface layer. And this, for instance, can be roughly captured by the continuum model, but there we really need atomistic simulations.
Thank you.
Or something close, coarse-grained, whatever.
Right. So next question is somewhat related. How can you attach a bacterium to the AFM cantilever without affecting its mechanical properties?
Well, the bacteria are quite large. They are diameter of 1 micron in our system. Therefore, we would like to do these experiments also with viruses, but they are just a few orders of magnitude smaller. And so the contact area is small. And if you have the bacterium attached here on the cantilever, there's one side that might be affected, but indeed, I mean, it's somehow glued, or you can attach a vacuum on that side. So there it is affected, but on the other side, where we measure the adhesion, it should not be affected. And we can also change, for instance, the ionic strength of the surroundings, so the turgor pressure changes. But then we really have to push hard to see that, because the outer protein, I call it fur, the protein fur of the bacterium is much softer. It's like with a teddy bear. So the teddy bear has a fur, and the rest has an elasticity that is much stiffer than the rest. So the turgor pressure helps us here, that we can glue and grab this bacterium.
The next question is, have you looked at membrane protein interactions with hydrophobin bilayers for self-incorporation?
Underway. That is underway, yes. We haven't looked, I can't say we have already looked at, but we have all the ingredients, we have started experiments, and many of them do not work, yes.
Do you have a suggestion for easily, that's easily in quotes, measuring adhesion forces of protein cells onto synthetic vesicles in water?
Adhesion forces of protein cells, of proteins or cells.
Protein or cells, yeah.
Well, if it's a cell to a cell, it might be easier, because you can possibly see it with some kind of microscopy that is connected with an AFM. Adhesion forces of proteins onto synthetic cells, then I would cover my AFM tip with a protein and then try to press on the synthetic vesicle. However, one difficulty is the synthetic vesicle must somehow be immobilized. So possibly another technique would be a optical tweezer, for instance, if you push cell into cells, or like as we did it with the bacteria, put the cell, if it's possible, on a cantilever and then push to the immobilized synthetic cell in water.
Okay, well, I think we're going to have to leave it there. Thank you again, Dr. Jacobs, for a wonderful presentation. And thank you all who are submitting questions. Again, we will try to get responses for these, the ones that have not been answered already, offline. So thank you again.
Thank you.
So the next presentation is going to be by Dr. Michael Grunze. This is a program highlight, so we're going to change tracks just a little bit. Dr. Grunze is the former chair and emeritus professor at the Institute of Applied Physical Chemistry at the University of Heidelberg. And since the start of the Max Planck School, Matter to Life in 2018, one of the fellows. His research interests include surface chemistry and interface physics, biocompatible surface coatings, adhesion science, self-assembly of organic mono and multilayers, X-ray absorption and X-ray emission spectroscopy, X-ray microscopy, inline holography, and biochemical sensors. Dr. Grunze received his PhD in physical chemistry from the Freie Universität Berlin and did his postdoc research at the University of Munich and Queen Mary College, University of London. The title of his program highlight is on the Max Planck Matter to Life School. It's a pleasure to welcome Dr. Grunze.
So good morning or good evening to everybody. I'm very happy to have the opportunity to introduce to you the Max Planck School Matter to Life in the next 15 minutes. The idea of the Max Planck School originates for quite a while, but it was finally realized in 2018, and the Max Planck Society started with 3 pilot schools, which are the Max Planck School of Cognition, the Max Planck School of Matter to Life, which I will address in a moment, and the Max Planck School of Photonics. Max Planck School Matter of Life is a novel program, and it's something new in Germany, because here directly 3 of the leading universities in Germany are cooperating with the Max Planck Society and with several Max Planck institutes. And the idea is to educate people and students, of course, such that they are capable and knowledgeable to work in the whole research area of Matter to Life. And I will detail that in a moment. Also, what is new is that it will be the first PhD program in Germany, which is a joint degree from several universities. So students attending the school in Heidelberg, when they graduate, they will get a degree also from Heidelberg, from Göttingen, and hopefully Munich. Excuse me. Now, what is our mission and what do we want to achieve? First, of course, if you are working in such a multidisciplinary and interdisciplinary area, you have to really support open-mindedness and collaborations, and also make sure that people can, from different scientific areas, can communicate properly. Often we have a barrier in understanding our colleague from the physics department or biology department or vice versa. The ultimate idea is within the school, and of course with the research and the PhD work being done, we would like to answer some very challenging questions, which are identify and analyze building blocks for engineering life. So we would like to know what are the basic essential ingredients to engineer a system which we could call living. that leads us automatically to the question, what exactly is life? How do we define life? How can we describe it quantitatively? And then ultimately, can lifelike systems be engineered? And if you go in the literature, you see, and you start some reading, that this is actually a question which has been around for a long time. Boltzmann thought about it, and then a very nice documentation about the ideas and the exchange of ideas is given in this little book by Schrödinger, What is Life? That's exactly what we are asking. He gave lectures at the Dublin Institute of Advanced Studies, at Trinity College in Cambridge, University Press published it in 1944. So anybody who would like to get a glimpse of the complexity of this question, what exactly is life, I recommend to get this little booklet and read it. Now, if we want to build something like a system which we consider lifelike, of course, then we have to think about Richard Feynman's quote, who said, "What I cannot create, I do not understand." So obviously, first, we have to understand the necessary details in living systems. Like I said, the fundamental, essential building blocks we need. And then we can hope to come to the point where we can actually synthesize something and start a big discussion. Is that lifelike or is it not yet? And what is missing? And what else should we do? But in order to get from the bottom to the topic, to the top of this diagram, simple diagram, we really, and this was shown by Joachim, but the other way around actually, he went down from understanding to synthesis. I go up here. We know from our own experience training students that if they studied a single discipline, let's say physics or chemistry or biology, it will take quite some time to develop the skills to communicate to the rest of the community and actually also to be productive collaborating. This is why our whole educational concept is really based and led by the idea that we have to provide the students coming in with a different bachelor, different areas, biology, physics, chemistry, and so on. And they all need sort of the same knowledge base before they can effectively work together. And the knowledge base required for what we are trying to do and you are trying to do consists of chemistry, biology, physics, molecular systems engineering, modeling, and so on and so forth. So we have a challenge here, obviously. We have the challenge that we have to combine all these different expertises in our school and also then somehow be able to give the students who are master students first in the first year and second year a great exposure to these different disciplines, so they learn the skills, the basic skills to understand their colleague in the laboratory. And the way that works here in the school is we are combining the expertise of scientists from different disciplines and research institutes, which actually supplement the knowledge, the basis of the other institutes. And that provides a very fruitful basis for good collaborations. So involved are the Max Planck Society, several institutes, Heidelberg University, Göttingen University, Technical University Munich, the Leibniz Institute for Interactive Materials in Aachen, the German Research Center in Heidelberg, the Heidelberg Institute of Theoretical Studies, and the Rheinisch-Westfälisch Technische Hochschule and Saarland University. So we get a group together with different expertise, different backgrounds, and different laboratories coming from different laboratories who are willing to work together, to collaborate on these big issues, these big questions, and also to join in together to educate the students. And I show you here a list of our fellows, and I'm not going to read all the names. I just would like to remark with sadness that Markus Motzkus in Heidelberg, he died this last December, And we are very, very sad that we have lost them. And but you see, there are people from the Heidelberg University. Then we have fellows from the Max Planck Institute. We have Aachen from the Leibniz Institute, colleagues to collaborate. And then, of course, University of Göttingen, the Max Planck Institute in Göttingen, Munich, University of Munich. You see some names you might recognize. Max Planck Institute, Biochemie, Petra Schwille. Karin Jacobs, you just heard this beautiful lecture she gave, and she's also part of our lecturing team when the students start. So she will participate in teaching physical chemistry. And then we also have a range of non-university fellows, which are different other Max Planck Institutes. So for instance, Reinhard Lipowski, he's also engaged in lecturing and teaching in the school. And you can look at the other names, and some of them you may recognize. Good. Now we have the educational missions. We talked about briefly the scientific mission on the questions we try to ask. Now from this automatically follows we have to train students to be effective and successful when they enter their master thesis and finally the PhD program. So we are looking for the best around the world. And we really don't care much what is their background in terms of their bachelor, as long as it comes from an area relevant to synthetic cells. So we have an international interdisciplinary master and PhD program. I say something about it in a moment. The joint degree we offer, which I think is unique, and students who succeed and get their degree can be very proud of it. There's a bracket around the Technical University of Munich. There are still negotiations how we can phrase that and how we can do the joint degree, but we are all very hopeful that this will happen this year. We have what I call actually a Corona compatible campus, virtual campus, which means all the lectures are actually recorded, and students who are sitting in the actual lecture in Heidelberg, for instance, listen to the lectures given in Göttingen and vice versa. So we have the lectures online and they're transmitted to our other locations, and anybody who is a member of the school can log in and look it up and has a record of it. The education is coordinated and performed by the fellows of the school, and they work very hard to mentor the students, to give them their personal, unrestricted, I would almost say, attention and help them with their problems, and also guide them sort of into a personalized curricula that basically happens in the second year when they're trying to find their, the area and a project which really suits their interest and their strength. Everything we do from the beginning, from teaching then to master degree and of course PhD, is focused on research and cutting edge research going on in our laboratories. And as a little bonus, we also provide housing for the students at the locations in Heidelberg and Göttingen. Okay, here you see one of the benefits and the beauty of our school, but also you realize immediately the problems we are having. If you look at the 10 students in Heidelberg, which were in the first cohort, starting in 2019, you see they come from all sort of countries. Taiwan, US, Ukraine, United Arab Emirates, Turkey, and Germany. And now you ask the question, what is their background? And you see most of them have a chemistry background. They got a BA in chemistry, but there are also students coming from biochemistry, material science, molecular biology, and chemical engineering. Now, you can probably easily see the point that people who studied molecular biology will have a very difficult time initially to grasp the concepts in statistics and physical chemistry, because they are just basically lacking much of the required mathematics and theoretical tools. The same applies for the chemistry students who probably have very little idea about molecular biology. And chemical engineers and material science and engineers bring another complete different set of skills into the school. But yet they all come with a different background. And the same is true also for our colleagues in Göttingen. You see it here. They also come from many different countries, and they also have a variety of majors. So we have to address this unevenness, I would call it, actually before they come. We would like to really start teaching the details of our subjects in the first semester. So we offer preparation courses before starting in September. That's all online. Then we have the welcome course, first week of September, where they meet and meet the fellows and have interdisciplinary courses, followed by the master program, 4 semesters, interdisciplinary courses in the first semester. Second semester, they're specialized and going into depth. Then we have lab rotations, third semester, and fourth semester is the master thesis. And that, if they get their masters with a good grade, they will get into the, be accepted into the 3 years of research, including mentoring, and they have then some individual soft courses. Am I running out of time? Looks like it. First semester, very briefly, we have practical courses and lectures in the core areas, and I'm not going to go into the details. They're all small classes, and in the second year they specialize depending on where they are, in Heidelberg, Göttingen, or Munich, in molecular system chemistry, complex systems, and biological physics, or bioengineering at the Technical University of Munich. I just flashed this up here. These are the faces, so they're real people behind the lecturing and teaching and mentoring in the first 2 years. And maybe you recognize some of the people. We can look them up in the recorded lecture and see it as a puzzle, you know, put the names on the different faces. Okay, then we have the third and fourth semester I talked about, the lab rotations and, excuse me, and preparation basically for the PhD phase, summer school. And this is really the application process. So if anybody of you interested to get into this 5-year combined master PhD program, like I said, eligibility requires the bachelor degree, and you should apply until December 1st this year. And I haven't talked about it, but you can find it on our webpage or by email. We are providing a generous financial, residential, and medical insurance support. Our research opportunities are outstanding and excellent. And I think Heidelberg, Göttingen, or Munich are very inspiring and unique settings. One more remark, who is sort of cautious and doesn't know if he really wants to do it, he can apply for what we call an undergraduate research opportunity, 10 weeks to work in one of our labs. And if we look at the applications we had this year, we have 83 bachelor, 11 master, and even 2 PhD students who decided to see if that is not something they would like to get into. So we are not discriminating by age. That's basically what I'm saying. We also, as a promotional thing and marketing, we have our webinar every Wednesday. Everybody is invited to look into it and listen to the talks. And we're listing the talks here, which were given this year by Joachim, Martin Möller, Henrik Dietz, Peter Komber, Petra Schwille, Eberhard Bodenschatz, and Laura Laporte. And it will be continued actually until the end of August, as much as I knew. And if you're interested to participate, just go here on the indicated webpage, and you will find the details how to register. Well, all I can say now is we hope to see you soon as a student, collaborator, or visitor. Down there's again the web address of our school, and there's also email address. If you have some questions or personal questions, we are very happy to answer. And look at the places, Heidelberg, Göttingen, and Munich. Don't you wish to be there now? Okay, thank you very much.
Thank you very much, Dr. Grunze. That was a very exciting presentation. The school sounds absolutely wonderful, and if I were a bit younger, I would apply.
Yeah, we are not discriminating.
Right.
Yeah.
So we have a couple of questions. I'll remark that we will have a short break after this, and we will resume again with the presentations at 1:30. But we do have time for a few questions. So the first one is, what are the financing options available for students aspiring to join this program?
If you're accepted into the school, be it Heidelberg or Göttingen, I mean, it's competitive, okay? We have a very competitive process, and I didn't talk about it, how our selection process goes. But if you're accepted, you're getting a very generous stipend, even during your master studies. We pay for all travel. You actually are invited for interview before you are accepted, and we come up for that. And the stipend is, for German student, unbelievably high. And if you are promoted, or if you then enter after 2 years the PhD program, that's further increased and equivalent to a full scientist position, basically, starting. So there's anybody can apply without any concerns about money, because even during the application process, we will help and make it possible that the people can apply even if they have no funds.
Okay. Is there a possibility for a PhD student to do a research exchange, something like a research stage where a PhD from another university gets the chance to pursue some of his or her research at the Max Planck Institute for Matter to Life?
Yes, of course. We are interested to collaborate with everybody. What I suggest is to write an email to our office or to me. You can find my email address on the webpage also. And then we will have to match you up with the right partner. I mean, that is ultimately the question. Can we find somebody who is interested in the project and has the space in the lab to accommodate you? But yes, there are several PhD students working in our laboratories from other universities.
Okay, great. Thank you very much. So we are out of time, and we are out of questions right now. So again, I would refer people to the website that Dr. Brunza has posted here if you're interested in applying or learning more about the school. And thank you very much again for a very nice presentation on what you're doing. It's very exciting, 21st century, cutting edge, interdisciplinary approach to education. It's wonderful to see.
Thank you very much. Thank you.
Okay, so we're going to take a short break for about 8 minutes. We will resume again with the final keynote presentation for today's session. And that will be at 10:30 Mountain Time and 6:30 p.m. Central European Time. So we will see you soon. So welcome back, everyone. It's time for the final presentation of today's session, which will be given by Dr. Joachim Spatz, one of the co-organizers of this meeting. Dr. Spatz is director of the Max Planck Institute for Medical Research in Heidelberg and heads the Department of Cellular Biophysics. He is also professor at Heidelberg University, as well as chair and founder of the Max Planck School Matter to Life. He studied physics in Ulm and at Colorado State University and obtained his doctorate in macromolecular sciences and completed his habilitation in physics at Ulm University. His research interests include cellular biophysics, material science, cell biology, interface science, and physics of soft matter. In 2009, he became a member of the Heidelberg Academy of Sciences and Humanities, and in 2016 was elected to the North Rhine-Westphalian Academy of Sciences. In 2017, he was recognized with the Leibniz Prize for his outstanding research at the boundaries of material sciences and cell biophysics. It's a great pleasure to welcome Dr. Spatz to give the final and keynote talk for today. The title is Bottom-Up Assembly of a Cell. Welcome, Dr. Spatz.
Susan, thank you very much for the introduction. And I will be happy now to present what my group is doing in the field of matter to life, or about more specifically the questions how to build a synthetic cell. But let me first introduce actually the group. And we have topics which are related to understanding living systems. And there was Tamadas, was a postdoc for many years in the group. He's now professor at India. He really looked into how cell migration, how collectivity between cells actually can be explained from a biological, but also biophysical point of view. And as you will see in one of the next slides, this really also motivates us to look into trying to synthesize something which we see here in a living system to see in a synthetic one. Then even more complex systems are organoids, which we are trying to approach. And there is Friedhelm Savane, who is looking into retina organoids and is able to grow them here in the group. Then on the more technical and the synthetic cell side, we have Ilya Platzman and Amelie Benck, who are leading how to build synthetic cells with different approaches. And one major aspect of the synthetic cell approach, which we are following, is a microfluidic technology, which I will introduce. And this was brought to the group by Ilya Platzman when he was starting his postdoc here at the MPI. And then many of these applications and questions are depending on the question how to functionalize biointerfaces. And there is, besides many others, Amelie and Fania very active in this. But besides the department, what you see here, we have then also department groups, which is my group, but then there are Heike Böhm and Ada Cavalcanti Adam, who are independent group members, who have their own group in the department, where Heike is actually the coordinator of the Max Planck School Matter to Life, which was introduced by Michael Grunze just in the last talk. And she's looking at biophysics of cellular interactions, especially interested in the function of hyaluronic acid. And Ada is investigating growth factor mechanobiology. She made very essential and major contributions the last years in the field of mechanobiology. Especially she was, for instance, looking at the crosstalk between integrins and BMP growth factors, which are responsible for growing bone at the end. Then besides being very interdisciplinary, we are also internationally, and the Max Planck Society offers a great opportunity to excellent postdocs who are leaving the group to actually establish a Max Planck partner group at their next career level. So like Judith, Diego and Tamal, they left the group and got positions in their hometown, home countries, and then applied for a Max Planck partner group, and essentially are still then linked with us to collaborate. But there is also a small budget which they can then spend on their side. So this is, let's say, the group we are, where the department on which basis we are collaborating and trying to eventually understand cellular systems different ways, but also trying to synthesize synthetic systems. And that's the question of why to build a cell, well, a synthetic cell. It's because it will enhance understanding of living systems. So by putting molecules together in a certain way, which plays a role in living cells, will boost our understanding on the living side. But on the other side, you might generate synthetic cells which have a functionality which even goes beyond cellular systems, like they could operate maybe at very extreme conditions. And at the end, it's also just great fun to be able to build something which is very functional. But let's start with living systems. And as I said, we looked for a couple of years now into collective cell migration. And collective cell migration is, for instance, very important in wound healing. And what you see here is a part of the skin, the cornea, the epidermis, and then the dermis. Within the dermis, you see single fibroblast cells. The nucleus is stained in blue, and then a lot of collagen. And then the epidermis, which is very specific, is that these cells are really making cell-cell contact. So in blue, again, you see the nucleus, and then you see somehow the membrane stained in kind of brown color, and they make cell-cell contacts. And this layer, the epidermis, somehow raised our interest, because while a dermatologist would look now from the side, as you see here, we started to look from the top. And if you look from the top, then you should now see a video, and you see that the top layer of the skin is under constant motion. And this constant motion actually can be described by so-called dynamic heterogeneity. Is very important for the skin eventually to be able to realize when a wound is created, and then that the collective makes decisions to migrate into the open wound. And there we then ask questions like, how do collectives make decisions? What prompts a cell to lead collectives? Is there any kind of hierarchy between cells? It's a very interesting topic, which mainly was addressed by Tamar Das, as I said, but also by Medhavi Vishwakarma, who is now a postdoc at Bristol University. So now just think about if you could do something, what you see here, synthetically. So build a compartment, eventually a cell is eventually a compartment, a very functional compartment, and then you put in molecules into this compartment, which eventually makes this compartment able to sense signals from outside that that can make decisions, maybe also collectively, that can respond to stimuli, and eventually can also construct, synthesize, for instance, collagen. And this is somehow opened, somehow this is bringing molecules together in a smart way, eventually to molecular engineer the system. And we started to look into this actually many, many years ago. That goes more than 10 years back now, where we started by a very conventional way. That we wanted simply to make a compartment which can adhere. And it should adhere via proteins, which are also responsible for adhesion of cells, which are making contacts to the extracellular matrix in vivo. And you see a compartment, which is a lipid membrane, and then you have integrins, and these integrins are transmembrane proteins, which are triggering adhesion to the extracellular matrix. And these integrins, we isolated from platelets. Then these integrins are actually called alpha-2b beta-3, a specific integrin from the large integrin family. And then they are stabilized in small vesicles. But eventually a cell has a size of a couple of tens of microns. So you want to have them also larger. What do you do then? You fuse these small vesicles by an electric field in close proximity to a platinum wire, which makes them to be giant vesicles. And eventually we were successful to the point that we saw these giant vesicles here at the interface to such a platinum wire. We stained the lipids in green, and we stained the integrins in blue, and also by just looking at the interface, it looks like there's adhesion. But what you see here was actually the work which we could obtain after 5 years. So very difficult, very complex biochemistry, which we underwent. And if you think about the complexity of a real living cell, so there's not just integrin, there are many, many more proteins involved, eventually will make it very difficult to make the system even more complex, because eventually when what we see here is an event that the cell is adhering, but many of these vesicles are actually rupturing at the interface. And why do they rupture? Because these GOVs are eventually mechanically too weak to build it up, bottom up, step by step. And that made us actually to nearly close this topic But then we, by a parallel project, we looked into microfluidics, where Ilya Platzman started to create water droplets in an oil phase. So nothing related at this point with proteins or with cells. And these very conventional water droplets in oil are stabilized by a macromolecule. The macromolecule is actually a dry block copolymer, where one block is made of polyethylene glycol, the blue one, and the green one is polyfluorinated polyether. So it's an amphiphilic polymer where polyethylene glycol likes water very much, while the perfluorinated polyether likes oil very much. And if you now bring these molecules at the water-oil interface, like done here with these channels, you have here a micron-sized channel where on one is water, and then the two perpendicular ones, oil is flushing in, and oil-water meets here at the interface. Water-oil is not miscible, but due to the amphiphilic polymer, which is dissolved in the oil phase, you generate here compartments, water droplets. So these droplets are filled with water immersed in an oil phase, and we generate here 6,000 droplets per second. So it's a mass production, and that's a very conventional way of making compartments, which is used in many different applications since 30 years by different groups worldwide. And we thought that eventually this can be used to build a synthetic cell. But what was somehow missing is that these polymer compartments, as you see them here on the left, are not very functional because molecules are missing. So we were looking for a technique which allows us to pico-inject actually molecules, to inject molecules into these compartments by a very quantitative and controlled manner. And this was then a collaboration within Maxim Bio, especially the group from Ewald Bodenschatz in Göttingen, who helped us establishing this pico-injection microfluidics. And you see a video where a droplet is passing a side channel, and the side channel is filled with a black ink in this case. And when the droplet is passing, it's injecting a certain volume of liquid into the droplet. And this is triggered by these two electrodes, which you see on the top. The two electrodes are generating an electric field. This electric field makes this membrane, the polymer membrane, porous, and a little bit of side pressure, overpressure from the side channel allows to inject liquids in a quantitative manner into these droplets. And that can even be parallelized. And I said it's really quantitative, so you know how many molecules are going into these compartments. Like you can, for instance, have here we filled actin and labeled actin with 3 different colors just to demonstrate parallelization. And then you get green actin, yellow actin, and red actin within one droplet. So that's a very helpful technique eventually. And once you have then have these droplets and you start to functionalize them, there are different ways to interface molecules with the rim of such a compartment. Like, for instance, you could add here gold nanoparticles like Ilya did, or you can add here NTA and then bind via his tags proteins to the interface. In this case, it was GFP, fluorescent protein. And since this functionality was giving at the interface of polyethylene glycol, you see that the rim is lightening up by the green color. If we don't carry any functional groups along polyethylene glycol, then GFP is simply homogeneously dissolved within the droplets. So you can play with these functionalities. You can now start to, for instance, first spread a lipid membrane at the interface of the polymer membrane. You can then pico-inject molecules, nanoparticles, proteins, which are distributed in small vesicles, and then see how these molecules are self-organizing at the interface of this water droplet. And there's an example here of spreading a membrane at the interface. At the end, it's an interface at which the lipid membranes, if the charge is correctly given, eventually spreads here at the interface. You see here giant vesicles dissolved, and here you see small, on the right side, small vesicles, and if they approach the interface, you maybe can recognize how they are spreading and forming a lipid bilayer. And we know from different experiments that it's really a lipid bilayer, so that you can measure the diffusion rates of the lipids, for instance. And I stressed at the beginning that the mechanical stability of these compartments are very important to eventually build up a synthetic cell bottom up. And this mechanical stability, for instance, you can quantify by looking at the diffusion of molecules which are bound to the interface. And if we bind them directly to the macromolecular compartment, like done here, and then we bleach an area and look at the recovery, you see that the recovery happens very slowly. While if we take the lipid, if we functionalize the lipid membrane, see at the bottom, then the lipid membrane is mechanically much weaker. It's stabilized through the outer shell. Then you see that the recovery is much faster, and the diffusivity of the lipid membrane is the same as expected in a freestanding GUV. Now, what can you do with it? And one example was, for instance, we were looking into microtubule organization, and this is now an example where this pico injection is really essential, because pico injection allows you to sequentially add proteins at a certain time point under certain conditions to the compartment. And you do not actually need to mix everything at the beginning in the water phase as we see at the bottom. And what we eventually want to achieve, we want to achieve a lipid membrane on the inner side of the water droplet, and then organize microtubules. But the biochemistry of this lipid bilayer spreading and the formation of microtubules is very different. So if we add everything here, mix everything together, then eventually what you see are microtubules. These are the green objects, but you also see just red spots, which are clusters of lipids, but it's not a continuous lipid bilayer, which is formed at the rim of the water droplet. So what we do is then we first form the lipid bilayer, and then we pico-inject the tubulin under different conditions. And then you see a continuously formed lipid bilayer in the red, and you see here microtubules very well organized in these individual compartments. That also allows us then to do dynamic experiments, like you can now lower and raise the temperature, which triggers then polymerization and depolymerization of microtubules. And then in combination with kinesin motors from Thomas Serret, you see how these actually spindle-like structures are formed. So spindles, as you see them also in living systems. And this arrangement and rearrangement is happening through cycles of temperature. Now we can form lipids, a lipid bilayer. We can include integrins. We can also add actin, and that's all in one cell. Eventually, then what you want to do is, this is now here still in the oil phase. The outside is oil, but if you want to interface now this synthetic cell with for instance, with another cell or with extracellular matrix, then you need to release it from the compartment. And this is happening by destabilizing now here the polymer shell by including small molecules as surfactants, and then the tension which is happening at the interface between water and the oil phase releases these now ready synthetic cell into the open space. And now it's mechanically much more stable than the ones you've seen before, because you have the essential players in the compartment. And then we were looking into integrin activation and adhesion, which is a major question in the field. And from living systems, the field knows a lot about how integrins are activated here. So they can be either from intracellular signaling or outside, like a ligand could bind, or a taline from the inside could bind to integrin tails and makes them a conformational change. And then if kindling comes, there's a cluster formed, an integrin cluster. So taline, kindling are known as very essential partners for integrin cluster formation in vivo. So we tried to build this synthetically. And we did this by using integrin, a taline head domain for activation of integrins, and then looking at adhesion. And then Lucia Benck could show in her PhD thesis that by increasing the concentration of taline, you see that the spreading is increasing in the interface against fibrinogen. And that means you can really control now quantitatively the activation of integrins, and you know the ratio between integrins and taline which you use, because you quantitatively include proteins into the synthetic cell. Now you even see integrin clustering, and this was a surprise that you see clustering of integrins even without kindling. Either we activate by manganese, as shown here, or by taline head. Now, eventually we want to, what we have right now, we have the integrins, we are included in the membrane and water on both sides. Eventually we want to also apply forces to the integrins via actin-myosin contraction. So we include actin, and then usually, well, in the cell you use taline to connect integrins with actin fibers. But taline is a very complicated, very large protein, very difficult to synthesize or to purify. I only know about 2 groups worldwide who can do this, so we cannot do this. But we do it differently. We form this link by a synthetic protein. And the synthetic protein is called DARPin. And DARPin is a technology which was invented by Andreas Plückthun in Zurich many years ago. And we collaborated with him to identify DARPins which have affinity to integrins and affinity to actin, for instance, or tubulin. And this is a very small protein, synthetic protein, where it can tune also affinity by changing small compositions of the synthetic protein, as shown here, the DARPin. And eventually we can identify a DARPin activator. So this is then a certain synthetic protein which activates integrin adhesion. And you see a very nice adhesion of this integrin at this interface. And if we have a DARPin which is non-activating, you see just a spherical GOV at the interface. And so you can have then integrin activators of different intensity, depending on which DARPin you actually use or program. And then even with the synthetic protein, you also have some kind of integrin clusters, as you see them here. But beyond matrix adhesion, you can also generate cell-cell interactions by using E-caterines in the membrane. You see how these vesicles then adhering to each other. Or you can combine now a synthetic cell with a natural cell. You see in gray a natural monolayer, and here in magenta a synthetic cell, and the magnetic cell is filled with iron nanoparticles which are magnetic. And this has been done by Friedhelm Savane. And then this is what is nice, you can now interface and provide proteins which bind to the natural cells, but by applying a magnetic field, as you see here, you can then start to elongate these synthetic cell because they are the magnetic particles in there, and you can apply tension to the neighboring. So you include a phantom cell somehow which can interact with the in vivo situation. I want to conclude. I also want to acknowledge some of the people involved. I also mentioned some, but many of my collaboration actually started with Benny Geiger, with whom we have a collaboration tens of years, and this idea of synthetic cells originated from discussions with him. Then at Bristol University, we collaborate with Imre Berger, also on the synthetic exosomes, and there are many people involved, PhD students, postdocs, in this area of synthetic cells, and especially I want to name Ilya, Amelie, and Oscar, who really did very nice, successful work the last years. And with this, I finish, and I've just finished with also acknowledging our financial contributions. Thank you very much.
Thank you so much, Dr. Spatz. We have some time for questions, and there are quite a few of them. So we'll go ahead and get started. The first one is, how do you induce actin polymerization within a GUV?
So actin polymerization was induced by, well, you include actin, you include also mini filaments of actin, and then ATP in order to trigger ATP polymerization.
Thank you. Asymmetry is a key aspect of the functionality of living cells. Injection of functional components occurs in your elongated droplets as they pass through the microfluidic channel, yet the synthetic cells are presented with isotropic spherical morphologies after collection. So then there are two questions. The first is it possible to arrest the elongated morphology as the droplets pass through the channel so that they are collected as anisotropic objects? And then there's a second question, can you inject at both the leading edge and tail of the same traveling droplet to generate asymmetry in membrane-anchored functional components?
So if I understood it well, the first question was if we can eventually generate out of the microfluidic channel water droplets which are not spherical but elongated. And we cannot do this, but there are ways to do this. And there will be, I think, a talk by Laura Delaporte, I think tomorrow. And I don't know what she will talk about, but she will eventually show you how this is possible. It's possible, and it's very nice work what they do. The second question, if I understood well, is if we can
both the leading edge and tail of the same traveling droplet to generate asymmetry.
Say it again, I didn't hear that.
Can you inject at both the leading edge and tail of the same traveling droplet to generate asymmetry in membrane-anchored functional components?
So you can generate asymmetry across the membrane, so you can functionalize the inside differently than the outside, but that's obvious. And now the question is if we can have some functionality at the big. Well, we never tried this. So I cannot really answer this. I think maybe it could be possible, but I need to think about that. Yeah.
Would it be reasonably possible to create artificial cells specialized as factories for individual proteins or protein families or other biochemicals in the near future?
Well, you can include into synthetic cells already a machinery which synthesizes proteins. So, for instance, you can generate GFP. You can synthesize GFP in synthetic cells. You can even include full nuclei. So you can isolate nucleus from living cells and include them, and making it still able to synthesize mRNA in synthetic cells. So I think that's feasible, and also I think that's on the way, I would say.
What makes the DSGUVs released from the oil phase into the aqueous more stable or robust than those prepared by methods? Doesn't the block copolymer dissociate from the lipids in aqueous solution, leaving a normal GUV?
So what you find is if you have a plain GUV, it's mechanically less stable, and if you have a GUV with transmembrane proteins, or even with more components like actin or microtubules. And so what we produce within the mechanical stability of a oil stabilized water droplet, we make this GUV more and more mechanically stable, and then we release it into the water phase, which eventually is then more stable than the pure GUV.
A somewhat related question, making droplets with microfluidics is tricky and requires a certain amount of time to stabilize the droplet generation. Pico injection seems more sophisticated system. How easy or difficult do you find this setup to install and work with?
So the microfluidic system itself is a very general technology these days. It's applied to many different applications, many different ways. hundreds of groups around the world are using it. So and the success of microfluidics is built actually that it's very usable and easy to use, and can be repeated. And the pico injection is a little bit more tricky. It needs more technique around, but also this is very reproducible and is also for certain applications where it's used in different labs. So therefore, we find it not easy, but we can. It's possible to operate it reproducibly, and both are very useful techniques.
There's a question about design. To what extent is the design of extracellular vesicles and proteoliposomes informed by computational methods?
We are not doing this yet, but it would be very useful. Well, we are starting to look into it a bit in collaboration. I think it's essentially, finally very important to combine it with computer simulations. Yeah.
How efficient is the release of the droplets from the oil phase to the aqueous phase?
That's a good question. Also, the success rate here varies. I think the very good ones obtain 80% success rate, but it could also maybe drop to 20%. That's about, so we are between 20 and 80% success rate. That's what I would say, depending on the vesicles you are also using.
Thank you. How much control do you have over the orientation of integral membrane proteins reconstituted into your synthetic cells?
So for instance, taking the integrins which we are using, you have actually little control. I assume that the orientation in our GOVs is 50-50. We are checking this right now by electron microscopy. So if you can somehow, if you find ways to include transmembrane proteins already oriented in small, but during purification in small vesicles, and then assuming that they all spread in the same way and being included into the GOV membrane, then you might get control over the orientation.
Another question about control. Once the liposomes are released from the oil phase, are you able to lead them back into the oil phase to perform further injections, or is the release the last possible manipulation step?
So we never tried to include them again into the oil phase. I think that's probably very difficult. It then gets probably contaminated. I would say after the release, you do not inject any more molecules into the system.
Could it be possible to stabilize a GUV intracellularly, either with a protein or an additional layer, in order to convey a different stiffness or even alter the lipid diffusion rate?
So the question is if we can do this in cells, is that right?
Intracellularly, yes.
Intracellularly. So you can tune the mechanical properties of these GOVs by assembling different protein shells at the interface. So that's possible. To trigger this intracellularly at a certain time point, I think is very tricky. At least probably you can use light, or you need a trigger somehow which causes then the assembly. I would say very difficult. I have not a solution for this, but maybe possible. Yeah.
Okay. Is there a limit to the size of objects that you can inject into the droplets by pico injection? And if yes, what is the order of magnitude?
So we injected single molecules, and we injected also microparticles of 1-2 micrometers. And that's the range we were operating so far.
How does the osmotic stress affect the stability of released GUVs?
It's affect osmotic pressure.
Osmotic stress, yeah.
Osmotic stress is affecting the stability. which
So
you
how does it,
which you need to take control over it. So you need to be aware of it and maybe adjust your system that they do not rupture or dissolve uncontrolled. Yeah.
So I think we'll end with two biological questions. Are the GUVs, can the GUVs be used to study complex metabolic pathways, which are generally difficult to study in vivo?
I think so. We haven't done this really. If you look at work, what Tobias Erb, for instance, is doing in the MPI in Münster, in Marburg, you eventually can create a minimal system, and you can also, you know exactly what contributions you have in the GUVs, which allows you to get more knowledge about metabolic pathways as in more complex systems.
Okay, and the final question would be, how do the size of your synthetic extracellular vesicles compare with the wound healing vesicles found in human serum?
They are about similar. Maybe our ones are a bit larger, but we can make them very small to 1 to 2 micrometers. So they are approximately the same size, I would say.
Okay. Well, thank you very much. Thank you. There are a lot more questions, but I think we're going to leave it here. Thank you very much, Dr. Spatz, for your very nice presentation. I'd like to thank all of our 4 distinguished speakers, Drs. Lepowski, Jacobs, Grunze, and Spatz, for their superb and stimulating presentations. And thank you to all of our international participants for your excellent questions and participation. We're now going to go ahead and close the session for today. And we hope to see you all tomorrow for day 2 of the International Conference on Engineering Synthetic Cells and Organelles. Wish everyone a wonderful rest of the day or good evening, as the case may be in your time zone. Thank you all.
Thank you very much. Bye-bye.
Bye-bye.